Last week we saw these headlines. The Gulf Stream is dangerously close to tipping point. Ocean current is at its weakest for over 1,000 years due to climate change and could plunge Europe into a deep freeze. And then there was this one. An Atlantic current system that controls sea levels and heat waves is on the brink of collapse. Well, that sounds bad, but as we know, headline writers and scientific papers sometimes diverge in their grasp of the facts. So, what's really going on? Should anyone be panicking just yet? Let's have a look. In this video, first of all, I'm going to remind you how the Atlantic Ocean circulation works and what it does. Then I'm going to talk to you about what has come out of one specific paper launched last week, but also put it into the context of a number of other recent ones as well, a couple of which are arguably more important. And then finally, some thoughts and reflections on what it all means. So let's talk about the AMOC, which is the Atlantic Meridional Overturning Circulation. It's a key component of how our oceans behave and how they transfer heat around the globe in ways that some of us have rather come to rely on. The short version is that warm water near the surface flows northwards. There it cools, sinks, and then the colder deep water flows southward. This is a huge movement of water. The AMOC moves almost 20 million cubic meters of water per second. It makes a significant difference to the sea level along the northeast coast of the US and Canada. Indeed, when the flow was particularly weak in the winter of 2009-2010, there was a 13 centimetre sea level rise along the New York coastline. Not only that, it gives the northwest of Europe a warmer climate than would otherwise be the case, much warmer than other places at the same latitude. The heat moved by the AMOC represents more than 1 million gigawatts of energy, which is 100 times more than all of the energy used by humankind. So it's not surprising that it has a significant effect on the climate. Now, why does this happen? You tend to assume that water would pretty much stay in one place if you left it alone. And it probably would, but the climate doesn't leave it alone. It happens because of two different aspects: the effect of heat and the effect of salinity, saltiness. The warm water expands, so it's less dense than when it's cold and it stays on the surface. Warm water rises. The warm water from the subtropics travels north and then is cooled and through evaporation becomes saltier, which means that it becomes more dense. The cold, denser water sinks and then moves southwards again, taking various routes around the world to the point where it begins upwelling, rising back to the surface and beginning the process all over again. It's now believed that the process could be interrupted or even shut down by the effects of climate change. Now, that was first suggested as long ago as 1961 by Henry Stommel, who saw the potential for interactions between temperature and salinity. So, for instance, if freshwater inputs from a rapid melting of the Greenland ice sheet were to sufficiently freshen the water, reduce its salinity, then at some point it could reach a tipping point where the circulation would simply collapse. That may not be purely theoretical. Around 8,200 years ago, there was an abrupt climate event that brought cold and dry conditions to significant regions in the Northern Hemisphere, much larger a change than standard variability. In this paper from 2005, the 8K event, Cause and Consequences, they suggested that an ice wall holding back a huge lake in Canada collapsed as temperatures were warming from the emergence from the recent glaciation, as it was then. This deposited a load of fresh water into the North Atlantic. That interrupted the AMOC and caused a major cooling impact that shows up in the paleoclimatic records across North America, Greenland, and Europe. When you project with climate computer modelling what would be likely to happen should the AMOC shut down now, it comes out with the cooling of the entire Northern Hemisphere, with greater cooling, unsurprisingly, in the areas that currently benefit most from the status quo, which includes where I live. It suggests there would be major changes of rainfall patterns, increases in winter storms, sea level rise of about 50 centimetres around the North Atlantic basin. However, a 2018 paper by Chen and Tung argues that the effects of recent emissions of greenhouse gases might offset the expected impacts of an AMOC shutdown. The AMOC was significantly weakened in the period 1975 to 1998, for instance, and if the dynamic had been as expected, that should have resulted in the Northern Hemisphere cooling, which isn't remotely what happened. Instead, the AMOC minimum was a period of rapid surface warming. More generally, in the presence of greenhouse gas heating, the AMOC's dominant role changed from transporting surface heat northwards, warming Europe and North America, to storing heat in the deeper Atlantic, buffering surface warming for the planet as a whole. They said they didn't think the AMOC slowdown would continue. If you looked at the natural variability in recent history, the recent decline is reaching the minimum. If history repeats, then it should last for a couple of decades only. The AMOC is continually monitored in the Atlantic by the RAPID project, which uses 226 moored measuring instruments at 26.5 degrees north. But RAPID has been functional only since 2004, which is too short a period to be picking out trends. However, that's one of the questions the latest research has some input on. So now at last, let's turn to that. The new paper by Caesar et al. Compiles a range of proxy data reconstructions of the AMOC, some going back 1600 years. They represent different aspects: flow speed, heat transport, water mass. And what they consistently suggest is that there has been a significant decline in the AMOC in the 20th century, with the most recent decades being significantly weaker than any previous time in the series. In other words, taking it well outside the scope of normal variability and hence giving it the fingerprint of human-caused climate change. This data is the confirmation of the AMOC slowdown that has been consistently predicted by climate models. Not only that, but there's a specific piece of evidence that you would standardly find quite counterintuitive, but which the models predicted. And that's the existence of an area of cooling in the Northern Atlantic some refer to as the Cold Blob. I know these technical terms. On the face of it, the Cold Blob is a weird anomaly, because, everywhere's getting warmer except for this one bit. But it was predicted by computer models as a result of the slowdown of the AMOC. And it would be accompanied by a warmer area off the east coast of North America because, the heat that doesn't make it north has to go somewhere. Here's another view of the blob from the modelling forecast from the IPCC's AR5 report. According to NOAA, 2015 was the coldest year in that region since records began in 1880, even as it was the hottest year globally. So if the models have been right about that, what do they predict for whether and by how much the AMOC might decline in the future? According to the latest models, they suggest it might decline by 34 to 45% by the end of the century. Now, this isn't easy to model because the system's complex and there's numbers of additional factors that support the stability of the AMOC, but that uncertainty can cut both ways. In an article by Liu et al. 2017, overlooked possibility of a collapsed Atlantic Meridional overturning circulation in warming climate. They talked about the impact of salinity and the fact that the computer models may have a stability bias. They applied changes to better reproduce the salt concentrations of the ocean waters. Now, before the correction, the modelled circulation was relatively stable, declining by about 20% in response to a doubling of CO2. In the adjusted version, it broke down completely in the centuries that followed that doubling. Why does it do that? That paper I mentioned at the start by Henry Stommel in 1961 described the process. Normally there's a balance. Freshwater flows into the North Atlantic from rivers and melting ice. Salty seawater from the south balances this out. But if the current slows down, then there's less incoming salt and the surface ocean becomes fresher. The less salty water is not as dense, so it doesn't sink so easily. Since the sinking of water, the deep water formation, is the engine that drives the whole thing, then it weakens it even more until you cross a point of no return. The Science Media Centre website collected some reactions to the latest study by a number of experts in the field. They were clearly responding not just to the paper, but also a press release that specifically talked about the Gulf Stream, which the paper doesn't itself do. I haven't seen that press release, it's not linked. But anyway, Professor Tim Palmer, Royal Society Research Professor in Climate Physics at the University of Oxford, he said this: linking AMOC variability to the Gulf Stream, as stated in the press release, is somewhat misleading. The Gulf Stream is primarily a wind-driven ocean circulation, and there's no evidence that I'm aware of that the Gulf Stream is itself weakening. The extent to which AMOC variability affects European weather is a matter of great uncertainty, as there are many other drivers for variations in European weather, including atmospheric chaos. Overall, this is an interesting study and one that needs continued investigation. However, it shouldn't be over-interpreted. Dr. David Ferreira, Associate Professor in Meteorology at the University of Reading, said this: despite satellites, Argo floats and many other measurement devices deployed in the ocean today, we only have a sketchy view of a present-day AMOC, except in 2 locations in the North Atlantic where the arrays have been deployed. It's important to keep this in mind when considering this study. So you'd have to say those are 2 rather cautious, albeit respectful, voices in response to this paper. Not all the responses were so restrained or respectful. Pierre Gosselin, writing in the skeptic blog No Trick Zone, suggested the paper had been contradicted just days before it was even released. He pointed to this paper, a 30-year reconstruction of the Atlantic Meridional overturning circulation shows no decline, by Worthington et al. He said that it tells us there's been no decline, let alone a weakest state. Now, if you're a regular viewer of this channel, you should get this problem straight away. When partisans come across 2 studies where they believe one supports their pre-existing worldview and the other doesn't, if they dive straight on the one you would expect with no particular rationale and without taking the alternative one seriously, you know you're going to have to look carefully at what's going on. In this case, the simple fact is that one paper is looking at a longer time frame than the other, a much shorter one. The principal author of the study that they claim refutes Caesar et al. Tweeted this: since this has come up a lot with the paper just out by Caesar et al. In Nature Comms, our reconstruction is over a much shorter timescale, 1981 to 2015, and over that period actually agrees very well with some of the longer reconstructions from their study. In other words, the fact that it's been relatively stable in the last few decades doesn't actually mean that it's not at a historical low for that longer timeline. But you know, it is nevertheless an important counter to the headlines, the ones that implied we're right on the brink, with the implication from the graphs that things are in this rapidly deteriorating spiral with short-term implications we should all be desperately worried about. That isn't where that short-term study places us. The strength of the AMOC is not rapidly declining year by year, it's holding relatively steady. It's expected by the modelers to reduce by a significant percentage, not to collapse, by the end of the century. So that's all fine then. Well, you know, not so fast. There are some pointing out that we can't afford to entirely discount the possibility of something in the short term. Another study released last week pointed to the Beaufort Sea as potentially bringing problems. The Beaufort Sea is home to the Arctic Ocean's largest freshwater reservoir, the Beaufort Gyre, a massive wind-driven rotational current. Historically trapped in the swirl, ice has had more time to thicken than it does in other parts of the Arctic Ocean. But since the Arctic's warming faster than other parts of the planet, with steadily disappearing sea ice and the annual melting of 270 billion tons of ice from Greenland's ice cap, the gyre isn't functioning in quite the way that it normally would. This article in 2017 described how it's changed. During the second half of the 20th century, and most likely earlier, the gyre adhered to a cyclical pattern in which it would shift gears every 5 to 7 years and temporarily spin in a counterclockwise direction, expelling ice and fresh water into the eastern Arctic Ocean and the North Atlantic. But for more than a dozen years, this carousel of ice and increasingly fresh water has been spinning faster in its usual clockwise direction, all the while collecting more and more fresh water from three sources: melting sea ice, huge volumes of runoff flowing into the Arctic Ocean from Russian and North American rivers, and the relatively fresh water streaming in from the Bering Sea. This paper noted that as a result, the Gyre has increased its freshwater content by 40% over the last 2 decades. It's now 10% of all the fresh water in the Atlantic Ocean. A team of Los Alamos researchers and collaborators from the University of Washington and from NOAA studied a previous release event that took place between 1983 and 1995. Using virtual dye tracers and numeric modelling, they simulated the ocean circulation and followed the spread of the freshwater release. The experiment showed that, contrary to expectations, most of the fresh water reached the North Atlantic through a narrow set of passages between Canada and Greenland, known as the Canadian Archipelago. That model run was based on a historical release. Right now, the freshwater volume is a lot greater than it was then. And if that very large volume of fresh water was released into the North Atlantic, it could run significantly more interference with the balance of salinity and temperature that drives the AMOC. Exact impact? Unknown. This paper, Wanaka et al. 2012, suggests that the strength or otherwise of the AMOC has been a factor in previous variability, particularly in the medieval warm period and the Little Ice Age that followed it. We infer that the surface AMOC was relatively strong in medieval times, became weaker in the Little Ice Age, and strengthened again after circa AD 1940. We suggest that the surface component of the AMOC amplified the relatively warm conditions during the medieval climate anomaly and the relatively cool conditions during the Little Ice Age within the North Atlantic Ocean. One of several hypotheses on the cause of the Little Ice Age is precisely the sort of salinity impact of ice melting temperatures that we're discussing here. Maybe we'll be marking the next phase in global warming by skating on the Thames, as they did in the 17th and 18th centuries. But it's worth noting that Wanaka et al.'s inference about the strength of the AMOC seems to be contradicted by the proxy measures presented in the latest paper. This may be just a reflection of how hard it is to reach firm conclusions from hundreds of years ago about things like how strong currents were. So where does this leave us? In one sense, same place as always. The unknowns are such that people will leap onto whatever version suits them the best. I've seen people jumping to apocalyptic conclusions, and likewise others jumping to the conclusion that there's nothing to see. All conveniently the same conclusions as they always reach. My initial takes are the following. 1. The majority scientific opinion is still that the danger of short-term catastrophic tipping points is overblown. There are reasons to think that in the short term the system tends towards stability. And that's reflected in those expert responses to last week's paper. That's not the same as certainty. And there are potential realistic scenarios that could upset that stability, which would make life difficult for those affected, which would include me. 2. As mentioned, there's apparently a historical precedent for such an event 8,200 years ago. So that should tell you that this doesn't just live in the world of computer models, it's something we've seen before. So we need to understand the mechanics better than we currently do. 3. This is a good example of how real-world impacts from climate change can be kind of counterintuitive. All those people who, video their dogs running in the snow or brandish snowballs in debates, whatever, and say, it's cold, what happened to global warming then, eh? Well, as the science has been clear for some time, changes to the climate can have a variety of local effects. A 1 degree increase in global temperature doesn't mean that just wherever you currently live, you get the same climate as today, just 1 degree warmer. Now, it doesn't mean that catastrophists must be right. People whose natural inclination is to see the end of the world lurking behind every corner. Those people are not reliable narrators for any of this stuff because they jump to conclusions that are not currently supported by the mainstream science, and they do it because, temperamentally, it's just what they do. But likewise, having made the effort to find out what the skeptics were saying about these recent pieces of research, I wasn't hugely impressed, but it mainly seemed to focus on ad hominem attacks on one of the key researchers, which I haven't repeated here, as well as jumping onto a different paper with conclusions that its own author did not support. How is all this going to go? However much uncertainty there is on that question, one thing we know for sure is it won't look anything like the Hollywood version that was played out in the movie The Day After Tomorrow, which used the prospect of the collapse of the AMOC to suggest the onset of an instant ice age, buildings freezing instantly in flagrant disregard of the rules of thermodynamics. Keeping your cool means not losing your head over the nightmare of cheesy disaster movies or indeed excitable news website headlines.